Dear students, in this video, we will look into one example of aerodynamic method that we discussed in last video. Now, as we discussed in aerodynamic method, we will deal with lot of mass quantities or quantities of water vapors both near the surface and in the air. So here, this is the same question that we solved using energy budget method, but more information is available. So let us look into that. So we are asked to calculate the evaporation rate from an open water surface by aerodynamic method. Air temperature is given as 25 degrees Celsius, relative humidity is 40%, air temperature is 101.3 kilopascal, wind speed is 3 meter per second, and all these measurements are taken 2 meter above the water surface, and we can assume that surface roughness height is equal to 0.03 centimeter. So what is required in this question? Whenever we are asked evaporation rate is generally expressed in units of mm, since it's a rate per unit time, which could be day, second, hour, and so on. In last lecture, we derived that rate change of mass of water vapors in system is equal to 0.622 K square rho A EAS minus EAU2 divided by P into some terms of Z. Now, we also learned when we were looking into videos of energy budget that we can always write that dH dt times rho W into area if we are talking about some open container which is exposed to some radiation, and with the negative sign as dH by dt is always decreasing, that should be equal to rate change of mass of vapors into the system. Since dH by dt is negative, negative will make sure that mass of vapors in system is indeed increasing, and we write this quantity as E. So we write E rho WA equal to mv, and E can be calculated as m dot v rho WA. So to calculate E from this equation, we will also divide it by rho WA, and all the calculations we will do for 1 meter square, and given that any area, we can always extrapolate it to the required area on which we have to perform the calculation. So now let us see that what all the things that we know. So we need to find the following parameters or variables before we plug values into this equation. So in typical, when large number of parameters are involved, I would write all the variables of interest for which we need to know the value. So K rho A, EAS, EA, U2, and P, Z2, and Z1. So K we know is von Neumann constant whose value is given by 0.4. Rho A in this case is density of air, which we also discussed that if we know the temperature, which in this case is 25 degrees Celsius plus 273.15, to convert it to Kelvin, and once temperature is known, pressure is already known as 101.3 kilopascal. Using the ideal gas law, density of air can be calculated, and we did the same calculation in last example. So we can use same value as 1.19 kg per meter cube. Coming to EAS, this is the saturation vapor pressure at temperature corresponding to 25 degrees Celsius. Again, we know that we can calculate this in Pascal as 611 exponential 17.27 T 237.3 plus T, where T is in degrees Celsius. And after plugging the value of 25 degrees Celsius, this comes out to be around 3167 Pascal. Now coming to EA, we know the relative humidity as 40%. So if we know the saturation vapor pressure, we can calculate actual vapor pressure by simply multiplying the relative humidity by saturation vapor pressure, which would be 0.4 into 3167, and this comes out to be 1267 Pascal. U2 in this case is the velocity that we are measuring at certain height, and it is given that at 2 meter above the water surface, wind speed is measured as 3 meter per second, and that also means our Z2 is equal to 2 meter. Z1 in this case is 0.03 centimeter, and we can always convert it to meter, which would be 3 into 10 to the power minus 4 meter. And velocity corresponding to z1 is equal to 0, because the premise of this equation is based on the fact because there was a term of u2 minus u1 and we put u1 equal to 0 corresponding to height of z0. Now when all these values are known, what we can do, we can simply go forward and put all these values. So our m dot v comes out to be 0.622 into 0.4 square into 1.19 into 3 divided by 101.3 into 10 to the power 3 into 997, which is again density of water at 25 degrees Celsius. In absence of any information, assume it to be 1000 kg per meter cube. Is not going to change answer significantly. Here we will have log of 2, 3 into 10 to the power minus 4 square, and square should be outside, that is we have to take square of the entire log term, and this should be multiplied by EAS minus EA, and this answer comes out to be around 8.68 into 10 to the power minus 8 meter per second, which when we convert to mm per day comes out to be 7.45 mm per day. I know I am rushing through these calculations, but ultimately it's simply plugging these numbers and getting our rate estimates right. So notice that there would be an additional term of rho w, because instead of calculating mv, we are actually calculating E here, and E should include a term of rho w, and area already we have taken as 1 meter square. So if you compare it with the just energy budget method, our answer is fairly close. Last time we calculated it as 7.1 mm per day, and this time we are calculating 7.45 mm per day. But when we account for this, this is also a significant difference that we are noticing, and when we extrapolate it to lake, and there are small changes in the available moisture transportation conditions, these answers would have significant impact in terms of volume. Now we have looked too extreme. In one case we were completely discarding impact of the mass or difference in vapor density. In second case we were totally discarding the difference of or the availability of energy. For example, in aerodynamic we do not care about whether energy is available or not. So both methods have their limitations. In next video we will combine aerodynamic and energy budget method to look into the more realistic estimates of evaporation. On the other hand, this method, that is aerodynamic method, is one of the widely used methods to estimate evaporation as well as evapotranspiration, and we will talk about evapotranspiration soon. Thank you.